The goal is to convert the sun's energy into electricity. So how does that work? Well, there's a lot going on, but you can simplify all of that into a few basic principles that will help us to both understand how it works and to calculate how much of the energy we can get for ourselves. So the first thing that's really important is that the sun's energy comes down and hits the earth. If it's directly above you, then it's going to hit a square meter of ground with 1,000 watts of energy. And it'll do that, as it's above it. What our solar panels are supposed to do is take that 1,000 watts of energy and convert them into electricity. The solar panels first off have a certain efficiency, and so these solar panels are about 20% efficient, which means that if the sun is beating down on that solar panel with all of its intensity, then you'll get about 20%, so 200 watts per square meter. Now these solar panels are about 1.6 square meters, and so these are 265 watt panels. So the first major concept is how much energy is hitting the ground perpendicular to your panel. The second major concept is how much sun do you get per day. And so the government has volunteers around the country that have panels on the ground or something where they're measuring the amount of sun that's hitting per day. And if that panel just lays aimed at the sun, then you just simply count, kind of like these panels are doing. You just count how many hours or how much energy you get. And so there's lots of stuff going on. It's all kind of complicated, but it simplifies down to a single number that you can look up on the internet, and it'll tell you how many hours of full sun that you should get per day with your panels that are aimed south. In Indiana, where we are, we get 4.5 hours of sun per day average over the course of the year. At this time of year, we'll get about 2.5 hours average sun per day, and in the heat of the summer, we'll get about 6.5 hours of sun per day average. What does that mean? Well, that means when the sun's at the wrong angle and the sun is at the right angle, and then of course the sun goes back to bad angles again, all of the motion of the sun helps reduce that full power hours, and clouds reduce the full power hours. So on a rainy day, you get very little solar energy. On a sunny day like today, you get kind of the maximum that you can get. We have some clouds that are probably taking some of the intensity, but there you go. So all that complicated stuff simplifies this website. They give you the average amount of sun per day, per month, so you can go look at it by month, and then of course you get the yearly figure. That simple number, 4.5 hours, can be used with fixed panels aimed at a fixed angle to calculate how much energy you're going to get over the course of the year. So we have 265 watt panels here. If the average is 4.5 hours per day, then 4.5 times 265 watts is 1.2 kilowatts average per panel. And then there's 365 days a year. So you're somewhere around 500 kilowatt hours of solar energy per panel per year. And that can help you determine what your payback is and what your income is on the solar panels. Thank you. So we've talked about the simplistic math involved in calculating your investment return. But one of the things that we said in that prior segment was talking specifically about having the solar energy hit the panels perpendicular. And of course, with fixed panels, that really isn't going to happen very often. And so what we need to be able to do is to understand how much energy we're going to make with these solar panels when the sun is not hitting perpendicular to the panel. So in this very simple diagram, I've drawn the angles coming in at a 45. The sun's rays are hitting the panel at a 45-degree angle. and you know, it's basic geometry. So you've got a triangle here, and if this is 1,000 watts per square meter, then the component, which is vertical, is the cosine of that. So you multiply that 1,000 watts times the cosine of 45, so that the element that goes straight down, the perpendicular element that we're looking for, that is 0.707, or times this is 707 watts. And then when the 707 watts hits our 265 watt panel, at the efficiency that it is and the area that it is, then you could just replace that 1,000 with the 265. So how do you calculate the power expected with an angle coming in? You multiply the cosine of the angle times the capability of the panel, and that gives you, in this case, 187 watts. That's great. There's two angles. There's one angle for the fact that the sun is a certain height in the sky at noon, and there's another angle for what time of day it is. And so if I do this simple thing and see how easy it works, you're looking at the total height of this, and if I move it over to this 45-degree angle, you can see that it went down from the total height. And then if I put another angle on it, you can see that it's here, and if I go down here, you can see it goes down again. And so that's you know, you figure out how much it went down using the cosine of the angle. And so if I said that the sun is at a 45-degree angle in elevation, but it's also a 45-degree angle, say it's 10 o'clock in the morning, then you would multiply the 187 times the cosine of the other 45-degree angle. Sorry, they're both 45. And that would give you 132 watts. So we got two 45-degree angles, and we're at kind of half power. So that's the reality of how it works. And then as you integrate that over the day, every slice of time, you're generating so much power, and that's adding to your cumulative total. Then as you get through the day, you've acquired so much cumulative time. And if you take the panel out of it, you can ask, well, how many effective full power hours do I have? And that's the calculation we talked about in the previous segment. So in the winter, 2.5 hours in this location, and in the summer, 6.5 hours. Average year-round, it's coincidence that it's the average of the two, but year-round average here is around 4.5 hours. That's at the panel flat on the ground. How can I improve that performance? I would certainly not just go out and lay my panels flat on the ground. I must be able to take advantage of this knowing where the sun's coming from. So how do we do that? Number one, we start to understand the basics of how the sun travels around, how the earth travels around the sun. So up here I've drawn a very simple diagram, and there's many better diagrams, and I'll have a link to that in the bottom. But the earth has got its north-south axis, and then it's traveling on a plane that's 23-degree tilt, 23.6 degree tilt to the sun, so that in the summer, the northern hemisphere is getting hit with more light, and in the winter, the southern hemisphere gets hit with more light. And then you can see where that is. And so then in this diagram that I've got, you can see where the sun, if this diagram is the sun's position at any time during the year based at the equator. And you can see that on March 21st, the sun travels straight overhead, and it rises in the east and sets in the west, just like we were taught in school. But in the extreme end of summer and winter, then the sun comes in at a 23.6 degree angle, either north or south, depending on the time of year. And then you can see here the path of the sun overhead. And it doesn't quite reach directly overhead. So the circles coming out from the center are how far down the sun is from straight over your head. Every circle is 10 degrees. And then the compass on the far outside tells you the direction. And so by knowing where your panels are pointing, you can use this chart to figure out for any moment what the angle is to the elevation and what the angle is to the azimuth. And then those two angles, the cosine, can help you to determine how much power you're generating. So, the next chart shows in Indiana how this works. And so in Indiana, we can see where the sun's path is, and we can say that it rises and sets kind of similar to what it did at the equator, 23 degrees north, or 23 something degrees south of the equator is where it rises and sets. But as it goes overhead, it doesn't go directly overhead. And so it reaches these lower elevations depending on where we are on the planet. And so here, I've drawn a picture of the Earth, and I've got these solar panels, and in order to keep these solar panels pointing at the sun on March 21st, I need to have them kind of pointing straight to the perpendicular of the sun. And so for the equator, that's just laying it on the ground. That's pretty straightforward. But for Indiana, which is at 39 degrees north, I need to pick that panel up 39 degrees so that I can get 51 degrees pointing up to the elevation of 51 degrees. And then if I go all the way up to 80 degrees north, then I need to have the panel picked up at 80 degrees so that it is kind of aiming 10 degrees into the sky. 10 degrees to the horizon. So that position for a fixed panel is going to give you the best performance over the course of the year, because the sun's going to move 20 degrees up and it's going to move 20 degrees down, but 20 degrees is the least amount of sacrifice with this cosine. The cosine of 20 degrees is 93.93. So cosine of 20 degrees is 0.93. So you're losing about 7% loss of energy in one direction. Okay? So this is the key math that you need for fixed panel. And if you want to improve your performance over this basic fixed math, then you need to move to trackers. And trackers, we've just looked at the chart that shows where the sun is for any given time of the year. So now we can aim our tracker at those two angles that we talked about, the azimuth and the elevation, and that will allow us to maximize, or I should say minimize, the angles to the sun, and therefore minimize the losses coming from the cosine of those angles, and give us the maximum amount of energy recovery. But it comes at a cost, because you have to have the capability of moving the things. You have to have some means of tracking the sun. So there's certainly added cost involved. And we'll go into that later. Okay, so the first major point is, how does the sun make energy? And we've talked about that. The second major point is, how much solar light do you get per day? And that's been simplified for us and is easy for us to look up. And that helps us determine our financial payback. The third critical element is locating your solar panels in a place that captures as much of that solar energy as you can. Now, on here, you can learn from my mistakes. So I have now got 3 locations to talk about. And so the first is, we'll point at the barn. And when we look at the barn, we can see that the barn is getting shading. So today is January 20th. It is the second shortest day of the year, and it's right around noon. So we can see where the shade falls on the barn from the sun, and that limits some of the solar energy that's available to my solar panels. And it actually costs about 30 to 40% in the wintertime. And then in the summer, when the sun's above the trees, then I get lots and lots of solar power. The second location that we've done is, I've moved some panels with this phase 2. I've moved some panels from the shaded area over to here, and then this area is, on this property, has full sun year-round, only limited by these trees in June and July. But for the most part, there's no place on my property with better sun than right here. The third location that I've looked at is over here behind us, where we're building the solar trackers. And then these solar trackers will also have very good sun. They've been positioned, you can see the shade on the ground from the trees is just nipping at the heels. So those holes have been located so that they can get full sun year-round as much as possible. This final sequence of photographs shows the path of the sun. If you watch the shade of the flagpole, particularly the top of the flagpole, it's making the same shape as that polar diagram that we looked at earlier. Next, we'll look at the path of the sun across the sky, and again, we're on the second shortest day of the year, so we can see how the sun kind of stays low overhead and then sets. And then on that last day, how the energy from the inverter changes through the course of the day. Thank you. Look forward to talking to you on the next video.